Calculate your weight in newtons by multiplying your pounds by 4.45, and then calculate your mass in kilograms by taking your pounds and dividing by 2.2. All right, everybody got something? Okay. Here we go. We are going to find a gravitational force between you and the Earth. Okay. So here's you, that's a big U, and the Earth. Okay. So we're going to be using Newton's gravitational force equation. Okay. So G is 6.67 times 10 to the negative 11th. That's an always. I'll give that to you. It's a constant. Okay. M1. The M1 and M2, which one's which? It doesn't really matter. One's the U and one's the Earth. Okay. So you're going to take your kilograms that you just calculated, and then the Earth has a mass of 5.97 times 10 to the 24th kilograms. Okay. The radius. Okay, so R in this equation is the distance between the centers of the objects. That is going to be essentially the radius of the Earth. Because adding half of your height to the radius of the Earth is like adding a drop of water to the ocean and saying, I just raised the sea level. You okay with that? I bet it's nothing. Okay. So the radius of the Earth is 6.38 times 10 to the 6th meters. So I need everybody to get your calculator out. And we're going to make sure you know how to use your calculator. I'm just going to say the mass. You use whatever mass you had. I'm just going to use 100. Just keep things simple. Remember to square the radius. Okay. Now, in case you don't know how to do scientific notation on a calculator, if you have one of these TI Texas Instrument, most of them have an EE button that is located right here. You go second, and it's like right above the X to the negative 1. Okay. Some of you have like times 10 to the X. If you have a Casio, you're looking for the EXP button or times 10 to the X button. Okay. So you're going to type in 6.67 EE. That takes care of times 10 to the negative 11. Don't hit subtract, but hit negative 11. That takes care of that. Okay. If you have this type of calculator, a little rough, you're going to have to use parentheses like crazy. or doesn't like notation without parentheses. Okay. Remember to square the radius. If you get it right, you should see a number that is really close to what you calculated your newtons to be on Earth. Give me a thumbs up if you got something that matches. You make sure you
Oh wait.
I used mine.
Oh, I got 666 pounds. Is that should be good? I don't know. It should be the right answer. Yeah, it's not 620. Oh yeah, my Newton's was 667. I see that. You got 6,000.
On the road you do that. Just do like fences.
Me? No. You?
I'm on this one. I got.
I mean,
I'm on this there.
you won. I'm good. I'm great. Would you rather do times 4.45 or do all? Probably.
I was so
Can you
close.
differentiate? Can you differentiate?
Probably newer. Where would it be at?
It's like it's like
Be
under the ice.
Bang. Okay, I got it.
So now she's pushing this and that's
Oh. What happened? What?
yes.
Jay's not here. What? It's the coach.
If it's square, you're just taking equation, not linear equations.
All right, so real quick, weight and force of gravity, they are synonymous. Okay. This force of gravity, little g, is a special case for this. This we can use anywhere in the known universe. Okay, this is on or near the surface of the Earth. All right, with that?
Yeah.
Okay. So, we can take that to, oh, I guess before we do that. Try that one out. Have a conversation.
The radius is double, right?
Uh,
The radius is
All I know is race.
Probably.
Yeah. Videos on that.
Yeah. Yeah.
But
So it's radius. And then this is the system.
English makes no sense right now. She's like, that's fine. What are the
from one source?
I know. Are we like, and opinion based, is it information? Where do the quotes? I literally just checked it today, and it's just like one paragraph.
Let's do tomorrow, end of class.
No, tomorrow at night.
End of class, but she accepts it.
Okay. Is it gonna increase or decrease? Decrease. That makes sense, as you go away from the earth, it's gonna get less. So is that gonna be half or a quarter? Why a quarter? Okay, couple things. When it says above the surface of the earth, the distance R is talking about the distance from the center to the object. So if you're above the surface of the earth, you have to tack on the radius of the planet to the altitude. You all right with that? So watch yourself. So it's the distance between the centers. Good there? So when we did this, we essentially doubled the distance of separation. So because this is squared, it becomes a fourth. Good? How are we doing there? All right. One of the skills that you need to be able to do in this day and age is weed out extra information that you don't need. When you Google something, it spits out a lot of stuff. Even AI spits out a lot of stuff. You gotta know what's relevant and what's just noise. Wrong, but not needed. Okay? So given this list of information, how would you, what would you need to know to figure out how much you would weigh on Mars? Okay, so you would need half of this and that. The rest doesn't matter. Right there. So you've got that. That's just a constant. Mass of U, you have that. Mass of Mars and the radius, the distance of separation between you and the center. Good? Okay. All right, so the acceleration of gravity. We can use this equation or near surface of the Earth. All right with that? Okay. I can have a similar, so I've got mass times 9.8, which is the acceleration of gravity. I can have the same format, and I'm not going to call this G, I'm just going to call this acceleration of gravity in a general sense. Anywhere. You all right with that? And I'm going to set that up equal to that. Good with that? Okay, so here, M1, M2 doesn't really matter. We'll say U and Mars. What is this the mass of? U or Mars? Which one will experience the acceleration of gravity if dropped? U or Mars? Everybody say U? That'd be crazy. Whoa! Mars is just. Okay. So, this is the mass of U, which mathematically it's canceled out. So we get this expression for the acceleration of gravity anywhere in our known universe or on any planet. You okay with that? Okay. So go ahead and calculate the acceleration of gravity. Oh, real fast. Is everybody okay with G can be like put off the side or it can be put in the numerator? Like that's synonymous, one and the same. Okay. So calculate the acceleration of gravity on Mars. just for like show and tell, I did this equation for the Earth. And here's what I got. You keep working on your things. Did this right. This is not going to be your answer. This would be the Earth's answer for the acceleration of gravity. Acceleration of gravity on Earth. I'm going to use that equation. This is proof of concept. What did you find for the acceleration of gravity of Mars? 3.7. Does that correspond to movies that you've seen on Mars? Do that. Okay. Questions there? All right. Any questions? We're going to take a next step. Deal.
So the acceleration of gravity on Mars, that would stay constant?
Yep.
Like, so there would be a different one for each planet, you would say? And then
Yep.
that would just be the same?
Yep. For that planet. Yep. Get of that. That's the planet look like a football, and then it might be, but most of it is sure. Good? Done? All right. So we are now, next step here. You got gravity, you got the acceleration of gravity. All right, so you have the sun. You have the Earth. The Earth goes around the sun in a circular orbit. Do objects naturally want to move in a circular path? Objects naturally want to do what? In a straight line tangent of the circle. There was, what's enabling this to move in a circle? What is playing the role of centripetal force? For orbits, it's going to be gravity, the gravitational force. For a tennis ball, what was playing the role of centripetal force? Tension. Okay? So anytime you have an orbit, gravity is the thing playing the role of centripetal force. Okay with that? Okay? Now, so that's what you start with for orbits. Any type of orbit, orbiting thing. Okay? So now centripetal force, we know that is equal to mass times speed squared over the radius. Yes? And we know that gravitational force is equal to gravitational constant m1, m2 over r squared. Now I see some letters there that look very similar to each other. That might be able to be simplified. Okay, so which one's the Earth, the sun doesn't really matter. We'll say Earth, sun. But what is that? Is that the mass of the Earth? the mass of the sun, the mass of both of them. Hmm. Which object is moving with this speed? Earth or sun? Earth. So this is the mass of the Earth. You okay with that? So the mass of the Earth gets simplified. Okay? What does that mean in real life? The Earth is massless? I heard it whispered. The mass of orbiting object doesn't matter. Get there? Okay. Okay, question. What is that R? Talking about in general. Like when you see this in this equation, you're like, oh, that's going to be the radius of the circular path. That is going to be that distance there. Yes? Okay. In this equation, what is that R? When you see R in this equation, you're like, oh, that's the distance between centers of masses. Is that the radius of the sun? No. That is the distance between the center of the sun and the center of the earth. Does that make sense? Okay? Assume when they give you a distance between planets or stars or stuff, that it's going from the center to the center. You don't have to add the radii, the radius of the sun and the earth to that. It's going from center to center. So these are one and the same. So one, like that one gets canceled and one of those gets canceled. Okay? And so what you end up with is this expression. So these canceled out and I took the square root of both sides. Okay? So this is the speed required to maintain a circular orbit. Speed required to maintain a circular orbit. And this guy here is the mass of the center object. Good with that? Questions there? Okay, so the Earth has to have this certain speed in order for it, so it wants to move this way. Gravity's like, nope, stay in, nope, stay in, stay in, stay in, stay in, stay in, stay in, stay in. Okay? So let's use this to figure out, to verify that the period of the Earth's revolution around the sun is a year. break out your calculators. First, calculate the speed that the Earth has. Here's the value for G. $29,747 meters per second is the correct answer. If you did not get that, here are my guesses of what you messed up. Recognize the mass of the sun to the 30th. Okay, and you are using the distance from the Earth to the sun. You're using these two numbers and gravitational constant. And remember to take the square root. Just to let you know, 29,747 meters per second is roughly 60,000 miles per hour. So that's like 17 miles a second. From here to Indy in like 5 seconds. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, you're in Indy. That's pretty fast. Faster than anything we've made. Okay, good? Now, from here, anytime you're asked or given the period, we're going to use that equation. Okay, so calculate the period, heads up. Your unknown is in the denominator. Watch yourself. at 31,683,000. We'll just call that good. Rounding that. Okay, recognize you're solving for the denominator. You need to get this out of here and bring that over here. Okay, what's the unit on this? Seconds. Not very, we're not very familiar with that in terms of what could we convert that to? Let's convert it to days. What do you say? So we're going to divide that by 60 minutes, divided by 60 for hours, divided by 24 for days. I get 366.7 days. That's really sneaking close to 365.25 days. Rounding, and the Earth's orbit isn't quite perfect, but it's really sneaking close. It's perfect. Good with that? So, that is what your homework is going to look like tonight.